Alright everybody, welcome back. In this video we are going to look at material related to section 14 of Unit 1 for AP Calculus, connecting infinite limits and vertical asymptotes. A little bit of narrative here to kind of set us on the path. You can kind of read that yourself, but if you look at it, it says there are occasions where the value that a function approaches continues to grow without bound, either in a positive or negative direction. The function might be going up this way or going down this way, and growing in one of those directions without bound. In this situation, we're going to say that the limit either approaches infinity for this top case, and we certainly don't need to write the plus with the infinity, but I do occasionally do that. Or in this case, it's going down to the negative infinity. And here you see, 4 situations where that happens and how it's notated, the limit from the left and right approaching infinity or negative infinity. Okay. A few videos back, we talked about infinite discontinuities. In all of these situations, we would have an infinite discontinuity. Okay. And I also say here, saying that the limit equals plus infinity or minus infinity is a specific way of saying the limit does not exist. In earlier videos, we've looked at times when the limits did not exist, either because the left-hand limit and the right-hand limit weren't the same, that they didn't match up, or that the function was growing without bound like it does here. In both of those situations, to say the limit does not exist is sufficient. Me personally, I tend to like to indicate when I've got a limit that's going to infinity or negative infinity, which of those it's going to, rather than just saying that it doesn't exist. All right. Last thing it says here, we still need to think about left and right-hand limits agreeing. Excuse me, my voice is a little scratchy this morning. In order to determine the actual limit, if x is approaching some value c, and it's approaching positive infinity from both the left and the right, then we will say that the limit is positive infinity, is the most specific way we can refer to it. But if as the limit approaches, this c value, as x approaches this c value, if the limit approaches positive infinity from one side and negative infinity from the other, then it's the most specific and way that we can refer to that is by saying that the limit does not exist. So I always like to try to refer to it in the most specific way possible. Let's look at our first example here. Example 1, we're supposed to find the limit as x goes to 0 for each of the following. And so we're thinking about both the left and right-hand limits. Right here is where x is 0. It's this axis right here. So as I'm approaching 0 from the left, this function is increasing without bound. So it's approaching positive infinity. It's a really terrible infinity on my part. And then as it approaches 0 from the right, again, as x gets closer to 0 from this side, the function continues to grow without bound, so it's approaching positive infinity. Since those two agree, we can say in this case that the limit as x approaches 0 is positive infinity. That's the most specific declaration of what that limit is. All right, part B. Here's our axis where x is equal to 0. In this case, the limit as x goes to 0 from the left of the function is negative infinity, and the limit as x goes to 0 of the function from the right, also negative infinity. So in this case, we can declare that the limit as x goes to 0 of the function is negative infinity. All right. 2 more to look at here. In part C, the limit as x goes to 0 from the left. Well, now the function's going down. That's going towards negative infinity. And the limit as x goes to 0 from the right. in this case is positive infinity. So that goes up without bound. And so since these two don't agree, the left and right-hand limit don't agree, in this case we're going to say that the limit as x approaches 0 of the function does not exist. Okay. It looks like my pair here, I probably should have put in a bigger font. That's a little hard to read. That's the point 0, 5. So that tells us that the limit as x approaches 0 from the left of the function is 5. And the limit as x approaches 0 from the right, it's growing without bound, so it's approaching positive infinity. Since these two don't match, again, this is a situation where the limit as x approaches 0 of the function simply does not exist. All right, moving on. Example 2. Find the given limit using your graphing calculator. We've found limits on our graphing calculator using a table in the past, and that's what we're going to do here. So since we're trying to find the limit as x approaches 3, I'm going to build my table with 3 in the middle, and I'm going to look at x values that are close to 3 on both sides. So I'm going to go ahead and type this function into my calculator. I'm going to scroll my screen up a little bit, type this function into my calculator, and then build a table to help me determine what the limit is. Okay, so first, type my function into my y equals screen. And then I'm going to set up my table to be centered at 3 and count by 0.01. Then I'll look at my table and I'll scroll up. First I'm going to focus on the values to the left of 3. We've got negative 24.99, negative 49.99, and an error. And on my calculator, I can look at values a little further away. Notice we see the negative 1249, negative 1666. If we go even further away, you see we get smaller and smaller negative values. But what happens is, as x is getting closer and closer to 3, the y values that you see in this column are becoming larger and larger negative values until we get to 3. So from this side, the limit is approaching negative infinity. So the limit as x goes to 3 from the left of this function would be negative infinity. Looking at the rest of the data in our table, if we go to the right side now, a little too far, 5001, 2501, you see if we move away from here, we've got a similar situation. The numbers as we get closer and closer to 3 are growing bigger and bigger, but in this case now they're growing in the positive direction. So from this side it's approaching positive infinity. And so overall here, the limit as x goes to 3 of this function does not exist, since those limits do not match. All right, keep plugging forward because I'm going to try and keep this down to 2 videos, but this might end up being 3 if I'm moving slow. We'll see. The next thing we're going to talk about in this particular lesson is the concept of the vertical asymptote or infinite discontinuity. And we start with this question: how do we know if a function has a vertical asymptote? And it says here, if it's a ratio, we need to look for when the denominator is 0. If the denominator is 0, then the line x equals a is a vertical asymptote of the graph of the function if the limit from the right or the limit from the left. We've got both of these as possibilities, limit from the right or the limit from the left, approaches either positive or negative infinity. If we run into a situation when the denominator is 0 and these limits don't approach infinity, then we're going to have a removable discontinuity, but we'll talk about that a little bit more in the next video probably. All right, so let's look at these. Which of the following has a vertical asymptote at x equals 3? So we start with f of x equals 1 over x minus 3. So does this have a vertical asymptote at x equals 3? Now I could go ahead and make a table for this centered at 3 and see what happens with my limits. I've already got the table set up to be around 3, so I might as well use what I have. Does it look like these values are getting to be larger and larger negative values or positive values as I approach 3 from one side or the other? And you see here the limit as x goes to 3 from the left is negative infinity. Limit as x goes to 3 from the right is positive infinity. And therefore, yes, this function does have a vertical asymptote. Okay. The next one, g of x equals quantity x minus 3 over the quantity x minus 3 times the quantity x plus 2. If you think about how we did limits, if we were trying to find this limit, this would have been an indeterminate form, 0 over 0. The x minus 3's would have canceled out. And so the limit of this would have been the same as the limit as x goes to 3 of 1 over x plus 2. And therefore, the limit as x goes to 3 of this function is 1/5. So no, this one does not have a vertical asymptote. Same thing in h of x. If I tried to take that limit algebraically, again, it would be the indeterminate form 0 over 0 when I tried to substitute 3 in. So I would simplify that to the limit as x approaches 3 of the quantity x plus 11. Oops, that's a g of x. So the limit as x goes to 3 of h of x here is going to end up being 14. So no, there's not a vertical asymptote there either. If I tried to take the limit algebraically in the fourth part here, an x minus 3 we could cancel out an x minus 3 from both the numerator and denominator, and this would turn into the limit as x goes to 3 of x plus 11 over x minus 3. And you can verify this for yourself if you want to go and type this into your calculator, but the limit as x approaches 3 from the left is negative infinity, and the limit as x approaches 3 from the right here is positive infinity, and therefore this function does indeed have a vertical asymptote at x equals 3. All right, so that's about all that we have time for in this video. We're going to come back in the next video and go through a few examples of finding vertical asymptotes and how we can do that using limits. And so I'll see you next time for video 2 in section 1.14. Have a great rest of your day.